Hi, everyone. Good morning, good afternoon, good evening. I know we have people from all across the world here today. Thank you for joining us for our first session on day 2 of Azure Data Week on Azure Cosmos DB. We've got a great guest with us from the Cosmos DB team. So, Luis, I will let you go ahead and introduce yourself and get started.
Sounds good, and thank you so much. I hear a little bit of an echo. Is that okay?
You probably have multiple Crowdcast tabs open. So if you're not using one of them, I would close that.
Okay. All right, and hello and welcome everyone. My name is Luis Vasquez, and I work as a product manager in Azure Cosmos DB. So product management is the role that defines the roadmap, defines the different features that are going to be worked on a product, and works directly on the engineering team. So Cosmos DB is a database that is optimized for today's data-driven priorities. The priorities that we have identified that really define modern applications are just share. Most of them share the following qualities, which is they need global reach, right? Very rarely we'll see applications that will need to be confined to a single region in the world, and the internet being an open and public platform requires these applications to have to prioritize users in any point in the world equally. This is one of the requirements that is best addressed by the cloud, and especially a cloud product that uses a global distribution and a global sense, and a global presence. The next one is low latency. In the same way that modern applications are expected to be accessible at any point or in any locality in the world, they also need this real-time feeling, or this real-time reaction time. Most modern web applications have a standard benchmark of 60 milliseconds for loading everything that an interactive experience needs to load. Infinite ingestion is more of a capacity planning requirement, where when we start an application, we don't know what specific storage goal or what specific scale it's going to achieve. The systems that run behind it should be able to start small and then grow as the application needs it, or as the data needs it. In terms of security, there's also a requirement of, well, having to have a fully managed aspect in its security processes. Yeah, very in a cloud-based application world, it's normal to have security mechanisms that are fully managed by the cloud provider. So everything that the cloud provider should comply with, including certifications, including firewalls, including virtual networks, should be readily available and easy to use from an application perspective. It's a solved problem, and the cloud provider should have a way to deal with and provide the highest level of security available. In terms of data variety, it's rare to see a single kind of structure or a single kind of schema full data in most applications. It should be left to the developers. It should be left to the problem space to define the right kind of data that should be used for a given application. So supporting multiple types of data structures, of data formats, of query languages provides an advantage for these modern applications, and rarely will they be constrained by a single data format. And last but not least, modern applications require a degree of being prepared for predictive analytics. So transactional data not necessarily will only live in a transactional system and have this entire data movement process to move it to an analytical system. In predictive analytics, needs to be real time. It needs to have a way from an analytical from a transactional store to also be accessed by the analytical data processing engines. So the key scenarios that we'll focus on this talk will be transactional scenarios, real-time experiences, big data processing, and artificial intelligence, which we will illustrate, or I will illustrate through different examples and reference architectures. So just as a reminder of the data platform options that you can find on Azure, there's quite a few solutions that you can use today from that range from fully managed to infrastructure as a service, platform as a service, and serverless options. Azure Cosmos DB lands within the database and big data category, which is the database engines on the cloud for cloud native applications. And so managing and synchronizing data and around the world shouldn't be a challenge. It shouldn't be a task that required extensive knowledge of replication, extensive knowledge of multi-tenancy and distributed applications. In that regard, Cosmos DB addresses those needs by actually delivering a highly reliable, with a fast response time platform that provides and solves the data layer of any application. And we have different features around scalability, around global distribution, and around data consistency that allow us to do that. So some of the biggest scenarios in Cosmos DB is distributing data globally, basically putting your data where your users are. And this is delivered through all 55 plus Azure regions around the world. Building real-time experiences. This is especially useful in retail scenarios, in IoT scenarios. And this all relates to having a data access layer that provides a 60 millisecond response or less than that. And Cosmos DB addresses that by providing single point lookups around 10 milliseconds. So that's one of the areas that is solved by using a cloud component like Cosmos DB. This makes this database solution an ideal, pattern for gaming, for IoT, for e-commerce, all of the experiences that are pure data transactions that need to happen in a real-time scenario. And we have solutions that simplify development with the use of serverless architecture. This involves event-driven architectures and then application runtimes that can run on a single serverless platform like Azure Functions. For our analytics story, we use Apache Spark, which is one of the industry standards for data science and machine learning, due to its rich programming infrastructure, libraries, and its rich set of functions that allow for easy data exploration and data aggregation stories. And then Cosmos DB at the end provides a simple lift and shift story with no SQL data. This lift and shift story benefits from our implementation of multiple interfaces that relate to open source database technologies, which we will talk about in a second. So the following diagram summarizes Cosmos DB through the different interfaces, the different data formats, and at the bottom, the different
Luis, are you there?
Yes.
Okay, sorry. We just went quiet for a minute.
Yeah, sorry. There's like an audio on this slide, and I could hear it. Sorry about that. Okay, so going back to this diagram. So at the very top, we have 3 different layers. One of the layers, the layer at the top is, let me use the laser pointer. The layer at the top is the interfaces that you can use to connect directly to Cosmos DB. This is the front end. This is the this is the front end, say, mechanism that applications will interact directly with. So this choice directly relates to the choice of connector, the choice of programming language, and the query language choice that the application will use. And we have multiple options. The first option is etcd. This is the database that powers Kubernetes orchestrations, and this is an option that we have just enabled recently for our latest release within May. This allows you to connect your Kubernetes cluster and use the database engine that manages it and host that on a reliable platform, which is Cosmos DB, with its high availability and its low latency features. The next one is the Table API. The Table API is a service that's similar to the Azure storage tables, since it behaves in the same way for use of connectors and for the use of um, and for the data objects that are stored within it. The next one is Apache Cassandra, a database standard that was born in the open source space, and it provides key value pair access through very scalable architecture. So Apache Cassandra is it's a database engine that is meant to be used for replication. It's meant to be used for high fidelity consistency tuning. And the way we operate in Cosmos DB is as a managed service, fully managed service that abstracts away all of the logic around partitioning, all of the logic around replication and clustering that Cassandra needs, which makes it very easy to migrate onto Cosmos DB and stop managing infrastructure around the whole execution of the database and the operations of the database. The core or SQL API is what used to be known as Document DB, and this database engine is a JSON document database access engine that uses a SQL-like language and that uses a set of connectors that are first party to Microsoft. So this is not an open source engine. This is the Microsoft-based document query engine. Apache Spark is one of our recent additions to Cosmos DB, and it will be available for data analytics directly on top of Cosmos DB data. Additionally, we have MongoDB, and MongoDB is based on the MongoDB wire communication protocol. It's a database engine that is Cosmos DB's version of the MongoDB open source standard. And last but not least, we have the Gremlin standard, which is another Apache-based specification. And this specification is for graph data and graph data definition. So it's the industry standard for graph databases, which has most of the vendors for the graph database space in the database market. So depending on the choice of interface, you'll face a choice of data formats. So if you choose Table API or Cassandra, you will have a key value based database. If you choose Cassandra, you can use a column family database. If you choose the core API and MongoDB API, you will have a document-based access. And last but not least, if you choose the graph database, you will have the Gremlin standard, you will have access using the graph database. At the very bottom, we have the service features that are differentiating about Cosmos DB. The first one is turnkey global distribution, basically the ability to select any region in the world and then enable a database replica on it. And this database replica will run seamlessly, and the replication mechanism will be automated. Again, this allows you to take any Azure region in the world, any of the 55 and growing number of Azure regions in the world, and replicating your data so that it's available for minimal latency with the users from that region. It can also be used for failover or for disaster recovery planning, which in the case of an Azure region going down, which is itself a very rare case. You can be protected by having a failover backup region that can be promoted either to right region, or it can be run on a multi-master setting, which allows for fast recovery of any downtime or any outage within an Azure region. The next feature is elastic scale out of storage and throughput. And this speaks to the capacity management and the scale story of Cosmos DB. We use a horizontal partitioning system, which makes use of distributed systems to add on to the infrastructure that is running the database and increase the capacity in terms of storage and in terms of amount of requests that the database can handle at any point in time. We also make use of a standardized currency that abstracts away the resources that every single query needs to use to run. The currency that makes use of this is called the RU currency, or the request unit currency, and this is the main unit for throughput and capacity management in Cosmos DB. This is a unit that can change at any point within an hour, and it allows for fast scalability and reactive scalability to any sort of increase in demand or increase in database requests. The guaranteed low latency speaks to the expected parameters for how the service is running and what the uptime within a year that a service can have. Cosmos DB has multiple configurations for its infrastructural service capabilities, and the first configuration is running on a single master, multiple read replica infrastructure, and this allows for up to 4 nines of availability within a year. But our most available configuration is using a multi-master setting. In a multi-master setting, 2 Azure regions can be used for both. 2 or more Azure regions can be used for reads and write operations, and this will provide a 5.9 availability, which is a 99.999% availability. This configuration would provide a maximum downtime of 3 minutes within an entire year. So it's a highly reliable database service in that configuration. And critical applications benefit from having an expected amount of time for uptime, and this would greatly benefit towards that. We also have a way of providing predictable query response times. We have a benchmark that uses a 10 millisecond read and 10 millisecond write expectation for point read queries co-located within the same region. So this benchmark can be generalized towards other queries since that one particular query is the definition of a request unit. So in that regard, you can always expect queries that have the similar behavior to be to provide that level of that level of speed of access. So the next category is the 5 well-defined consistency models, and this defines the replication within the Cosmos DB infrastructure itself and amongst the other within itself and amongst the different Azure regions that are used within a global replication system. So if you add a new Azure region, the rules of how the data will be replicated will be based on the consistency models that are defined in the database account. And last but not least, we have SLAs on many categories, which provide comprehensive guarantees backed by the service level agreement contract. The guarantees are throughput, availability, consistency, and database security. So the following is an example of an application that uses Cosmos DB. We're going to answer the question, how can this be leveraged and what kind of benefits does it provide in a real application setting? So this application pattern is being used by different companies for e-commerce platforms and gaming platforms. Basically, you have a real-time data client or a real-time application. This real-time application will talk to a layer that routes the application behavior. And in this case, it's an application that can be distributed amongst many regions. Think about a database for uh, pizza ordering. If you have a pizza brand like Domino's Pizza that spans around multiple regions, even in a single country, you want to minimize the latency so that it provides the best front-end user experience ever. So you can have an application platform that is divided in different regions. Each region is located in a strategic place within a country or within a locality, which provide minimal latency between the application layer and the front-end client. Similarly, you may want to also use Cosmos DB to replicate the application and session state data to be as close as possible to every single one of the application regions. So the application regions can talk seamlessly with the database, and the database itself can return responses within less than 10 milliseconds. So this database to application layer is minimal in its latency, as well as the application to the browser. And the application is assuming that the database component is the same in every locality. So it assumes that the database has replicated already all of the data that other applications other application instances will be using. So the goals of this system is to minimize the latency for every user while still maintaining a consistent experience across database instances and across application instances. It's highly resilient for high availability if you have an additional region which can be run on a multi-master, on a single master, multiple read replicas. And this availability will guarantee a backup, or it will guarantee a backup, a secondary region that can be promoted to primary region in case it's needed. Another example is a pattern for multiple data access patterns or data access pipelines for either real-time data analytics or batch data analytics. So let's analyze it. So the example here is using a web-based application for e-commerce. And this web-based application is supposed to provide recommendations for the products that are being browsed through the e-commerce experience. So it captures the browsing behavior and then evaluates it against the recommendation engine. But at the same time, it sends a copy out to an offline data store. The path from the top is meant to serve real-time recommendations. So for example, if you're browsing different products, at the moment you're browsing them, you're provided with recommendations for the products that you last saw. So this is a database that is considered to be on the hot path. It provides recommendations on actions that originated seconds ago or milliseconds ago. In this case, this reference architecture uses Service Fabric to provide the decision engine, and it uses Cosmos DB to store the recommendations and then to retrieve the recommendations directly to the product page. Azure Data Factory is used to take those recommendations and send them down to an offline data store or a data lake, which provides cost-efficient storage over a long periods of time, and can be optimized for batch-based data access. The recommendations that come from the bottom side of this architecture are batch recommendations that are historical. So Apache Spark on HD Insight can take chunks of this data and then analyze it and provide more historical recommendations. So for example, at the top, you would get, well, this product that you're currently browsing, let's just say you're browsing t-shirts on a fashion e-commerce website. These pants are, let's say, trousers, would go very well with these t-shirts that you just browsed for. But at the bottom, you will get a recommendation or an insight like 100,000 users have bought this combination together within the past couple of years, right? So it provides a more historical, batch determined conclusion from the historical data. This historical data also keeps getting refreshed by the Azure Data Factory, and it keeps being appended to. In a similar way, we can see how Cosmos DB provides benefits for the IoT and gaming space. Gaming, especially in modern gaming applications, leverage a lot of multiplayer real-time features that require high-speed data access and require high-speed response times from both the content, the game logic, and the stats that the game generates. Think about a mobile application game. The company Next Games has built their mobile application, mobile multiplayer game called The Walking Dead on Cosmos DB. And the architectural pattern that they use is the following. They have a traffic router in the middle, and then they use Azure API apps to host the game logic and the game backend. The game logic is usually a stateless application component, and it uses a transitive set of properties, which just taking a request, process the request in a certain way, sometimes using random number generators, sometimes using feedback from other users, and then sends that to the database. The database obtains the entire state of all the actions that take place within the game, and this data can be sent to HD Insight for analytics. However, there are reactive patterns that are emerged from the game. If there are actions or sets of actions that align from different users, these actions will generate what needs to be a notification or a reactive, say, prompt from the game. Cosmos DB provides a mechanism that allows for event-driven processing, which based on an event pattern, it can directly source that event to different pieces of infrastructure, and then eventually sending connecting the services and probably sending a notification. For example, let's just say that weekly high score has been computed, and then you need to receive it on your phone saying that, oh, hey, you are number 10 of this week in this whatever game you're playing. So Cosmos DB will send that event. Azure Functions will detect the type of event, and then Notification Hub will be able to deliver the notification to the different front-end game engines. In a similar way, we integrate also Azure Content Development Network to process all the static files, say all of the graphics and all of the imagery that a game needs, which can be hosted on a blob storage for binary files. At the centerpiece of this infrastructure, it's Cosmos DB maintaining a consistent session state and maintaining a scalable architecture for every time the game increases in popularity. This is strategic to the operation of the game. The patterns that Next Game saw when they were running this game is that every time there was a new episode of The Walking Dead, the TV series, the game would increase in popularity and then decrease periodically, or decrease with a certain cool-off mechanism. So whenever the episodes would come out, this is a predictable event. They were able to increase the capacity flexibly using the request units notion. As a reminder, request units can have an hourly basis for its capacity planning. So you can change the request units at any hour. And then once the capacity is dealt with, you don't need that. You don't need to incur the cost of that capacity for the remaining of the operation of the game, or until there's another capacity spike. So it's possible to just reduce the capacity gradually and then not have to deal with any of the infrastructural implications of doing that. There is no need to remove a replica. There is no need to let's just say, reduce the computational infrastructural resources that deal with the database scale. You only have to interact and input for request units, and that will take care in the backend for all of the scale down aspects of the database engine. And one of the last pieces of architecture, reference architectures that I wanted to share relates to scale and telemetry. Telemetry systems and IoT systems are also some of the biggest customers of Cosmos DB and the biggest scenarios that benefit from its scalability story and from its automatic partitioning story. Think about the following example. An IoT device emits data, and the kind of data that the IoT device is more of a write-heavy, write-optimized data pattern. It emits data that is meant to be aggregated as a set and not necessarily processed individually. And every time it emits data, it can be routed using a IoT hub mechanism, which is basically a pipeline that sends data and formats it through the different channels. We use Apache Storm to serialize that data and make it a JSON document that can be ingested by Cosmos DB. And at the same time, we can use this routing mechanism, which will storage it in a blob storage archival component. Cosmos DB contains the telemetry and the device state, so it's a running series of data points that are continuously being inserted into the database. Every time there is the need to process an anomaly, Azure Web Jobs will take a set of that data and then analyze it. And then the result of the analysis will be either there is something wrong with the systems running in the car, in the case of Toyota, or the parameters are running on a set in the data time series is running on a within parameters that are normal. So if the web jobs detect a statistic anomaly, they can send the response back to logic apps, which will be routed through IoT Hub back to the car or back to the devices, and that will send a reaction. The reaction can be either send an alarm, set a signal, a warning system. And one of the examples that can run on this infrastructure is, let's just say that the engine overheats in a car. So the data will start emitting high values for temperature in the car engine. This will be routed from Apache Storm into the archival, so we have data to further analyze this or to further detect these patterns. And then the real-time data will be sent to Azure Cosmos DB, which will collect it. Azure Web Jobs will continue analyzing it, and Cosmos DB uses its event sourcing mechanism to send that data automatically to the web jobs. The jobs will just run standard statistical anomaly detection, which basically have a normalized parameter, a normalized trend of values for a certain system. Say the temperature of a car has very well-known parameters of how the values, the readings should be within. The web jobs will then detect the case where this falls out of the normalized values, and this will be called as an anomaly. Then that signal will be sent back to logic apps, and the car will have a device that will receive this signal and then turn on the warning sign for the overheated engine, or it can send a warning which will trigger a response from any service, let's just say like any repair service or any there's a term for this, but basically when you're stuck in and your car doesn't work and they need to send out help directly to you. So the systems are capable of doing that through this mechanism that processes the data that is sent in real time from the IoT devices. The real-time component is very important because these can be life-threatening, or these can be critical conclusions that need to be computed from the data from the systems. I know I said that was one of the last architectures that I was going to show, but this reference architecture heavily leverages serverless computing and it can provide a good example for how to integrate Azure Functions or other event-based reaction systems. So the following is how to use Azure Functions and the change feed, which is the event sourcing mechanism in Cosmos DB, to isolate separate logic and host it on a serverless architecture. So what kind of logic is best to be hosted on a serverless architecture is stateless applications or isolated units of logic that need to compute or make a computation and then send that down the chain. And in this case, it's serving an e-commerce setting. Let's just say that you can have a checkout experience that from the browser sends a request down to Azure Functions to serialize it, to enrich the data, and then send it to Cosmos DB to store the order events in the order that they're landing. In the same order, the change feed will be triggered, which will be consumed by a series of Azure functions, each one of them hosting an independent logic. The logic in the first part of the chain can be the tax logic, the second one can be the payment logic, and so on until you reach fulfillment of the order. So the advantages of keeping this logic isolated are the fact that they can be updated independently and they can be treated as microservices. And Cosmos DB naturally integrates with that by sourcing the events that these microservices will process. So this is an example that represents architectures being used by ASOS.com or Jet.com for their e-commerce platform systems, current users of Cosmos DB. Let me now skip down to an aggregate view of the value propositions of Cosmos DB so that we can talk about the specific features, and since we've covered enough examples and reference architectures. So again, going back to the interfaces, the data types, and the service features, Cosmos DB is a multi-layered system that is adaptable to any requirement for real-time and any requirement for serverless architectures, any requirement for IoT systems, and so on. Let's talk about the scale and throughput story. The way we can adapt to any system is by appending partitions and appending compute power. Appending partitions represents appending compute power and represents appending storage to a given database instance. So this allows you to scale from tens to hundreds of millions of requests per second across multiple regions. Every partition serves a given capacity in terms of computation and in terms of storage. So our way to adapt to any size of workload is by just appending the right number of partitions. The partitioning system will operate automatically, meaning that on the application end, you only need to define a partition key, and this partition key will be parsed automatically and then generate a distribution that is based on that partition key's statistical distribution. This partition key is hashed and computed automatically in the backend, so the application only needs to provide it with the data, and this component will be dealt with automatically. We use, as we mentioned, request units, which provides an abstraction over physical resources, which include RAM memory, include cores of processing cores, and storage, and disk I/O operations. And these resources are physically abstracted by this number called request units, which provide, first of all, a relief to a logistical challenge of determining the scale and the size of a database application, but also provide a way to adapt it to the 100 requests atomic number that best represent your application scale. This provides you the ability to say, if I have an application that requires 500 requests, I can tune it to go up to 600 or to go down to 400 without knowing what physical resource implications that has. It requires a lot of instrumentation, and it's almost not a deterministical process to measure that in other database systems. Traditionally, you would have to have instrumentation to tell how much RAM memory, how many seconds of a core, how many disk I/O operations a given query would take. And once you knew that, you could estimate your capacity and plan for that. But in Cosmos DB, we give that number automatically. So this allows you to understand your own workload and adapt to it better as you need it. In a similar way, this service doesn't have any tiers, and it doesn't have any, say, layers like premium layer or that provide different levels of resources. We only provide requests per second and storage as the main cost components, and this simplifies greatly the capacity management of any given database system. So based on the set of RUs that were configured, that's what's going to define the cost of the database, RUs and the storage that is included. Cosmos DB is also built on premium infrastructure. It uses SSD drives in the backend, and it uses dedicated networking, and it uses dedicated computation storage and computation layers. This allows you to have a guaranteed 10 millisecond read and write operation for the fundamental operations, and the distribution mechanism allows you to place your data as close as possible to your users. Speaking of which, you can have a turnkey global distribution aspect by just configuring the number of regions that your database can run on. And the interface that runs this is literally just a map where you can click all of the regions where you want your database to run at. Cosmos DB is available on all Azure regions, and Azure is the cloud provider that has the most number of data centers in the world. So it has more regions available for cloud services than Amazon and Google combined. And it keeps adding more regions. And the regions that you can use include geofence regions, they include government regions, they include within the same country different redundant geographical, redundant within a geography available regions. So, for example, there's a number of regions in the United States and backup regions for specific localities in the US. West US has West US 2, Central West US, and regular West US in the database region for different purposes. And setting up the different regions allow you to either have a manual or automatic failover based on the conditions that you set, or based on the conditions that determine if a region goes down from a Cosmos DB service perspective. We now have also 5 consistency models that allow to finely tune the database replication to the needs of the application. Most systems will provide strong or eventual consistency, where strong consistency is the mechanism where within replication, all of the replicas need to acknowledge the right operation before it can be completed. In this case, it's a very dependable, very strongly consistent configuration, because any replica will have always the latest version of the data, since it takes the time to replicate that data before it can be acknowledged. This has a trade-off of performance, because it really guarantees that the operations are, say, distributed across all replicas before they can be completed. On the other side of the spectrum, we have eventual consistency. And eventual consistency is a system, a configuration that prioritizes speed of operations. Any given replica can receive the right operation, and as soon as a given replica receives the operation, it'll be acknowledged as completed, which will improve the time of completion of the operation, but at the same time not provide any guarantees on the order or the, say, the availability of a given replica to the other databases. It's really hard to fit a scenario within these two extremes of the spectrum. So that's why Cosmos DB provides 3 different options in between. We have bounded staleness, which provides a predictable window of how many versions or how much time a database entry can be as old as. So it's less consistent than strong, but more consistent than the options to the right, and it's also faster than strong consistency. On the other side, we have consistent prefix, which behaves like eventual consistency, but it also provides a guarantee on the order. So the data can be, say, on any replica, the data is not guaranteed to be the latest, but it will always be in order, compared to eventual consistency, which prioritizes pure speed of transactions, but it doesn't provide any guarantees on the order or how late or the latest state of the data. And then session consistency provides a read your own rights behavior that can be used to mimic a single tenant, single database application. You establish a session, and that's what's going to keep the consistency for the applications that have established the sessions to themselves. Our availability of APIs keeps growing, so we always have new APIs and new ways to onboard applications to Cosmos DB. The APIs let you have your own choice, and your developers, it lets them have their own choice of drivers, as long as they are compliant with the standards of the open source technology that is implemented. And they can use their desired query language, their desired connectivity drivers, and even their desired database frameworks that they can use. So you can use things like Mongoose, which provides an object model for MongoDB operations. You can decide to use any sort of enrichment, any sort of frameworks that enrich the programmability and the developer friendliness of the application. The database engine that Cosmos DB provides standardizes all of the features, including automatic indexing, including automatic partitioning, and scale management. And this effectively offers a premium database service, like fully managed service, on all of the APIs. So you can perceive them as individual services that are hosted on a fully managed platform. Speaking of automatic indexing, one of the trade-offs of using a non-relational database is that since there's not a schema defined, the database engine does not have any hints to optimize for read operations. For this purpose, Cosmos DB uses an automatic indexing mechanism, which basically takes documents or any sort of non-relational data which has variable amount of properties and variable amount of values, and then makes an index that's a BW tree that standardizes this view. It provides a standardized view of all of the properties and all of the values that associate with the body of data that resides within a partition. And then this is automatically updated, and this will ease the cost and the time that it takes to process read queries. So for example, if you look at these set of products, you have different kinds of mugs and a Surface Book, right? There are properties that they share. For example, the Geek mug has a color of graphite, and the Surface Book has a color of gray. However, the mug doesn't have a CPU, nor memory, nor storage yet, but the Surface Book does have a CPU, a memory, and storage properties. So a non-relational store will keep the same namespace for the properties that are shared, but it will keep individual records with their own namespace, with their own properties that are different. So the index in Cosmos DB standardizes this view by using a tree representation. And the index is co-located with the database engine, so index transformation operations are minimal, and they are headless and enforced within the write operations of every database insert. This is synchronous, so it operates every time there's a new operation. And this can be configured. So there's index policies that can be enforced. So in case you have data that you don't query on any document, then it provides a way to optimize the index in terms of its storage. So the infrastructural capabilities of Cosmos DB allow us to provide comprehensive SLAs. We have SLAs on latency, meaning that our contract for the service level includes the milliseconds that it takes to process fundamental operations. A fundamental operation is a 1 kilobyte read or write document operation from the same region using its ID and its partition key. So for those, you're guaranteed that they will take always less than 10 milliseconds for both read and writes. High availability, depending on its different configurations, allow you to rely on the uptime of the database server, and that is also embedded in the service level agreement. The throughput to the level that it's set is also guaranteed, so you won't be receiving less request units than you are set within the service, which allows for high reliability on the scale of the service, especially when it changes. The scale can change at any point in time. And consistency is guaranteed on the parameters of the configuration setting that you choose out of the 5 different consistency models. This is one of the few financially backed service level agreements in Microsoft, meaning that any failure in the service level of any of these categories will be resulting in a financial retribution from Microsoft. So that's how reliable we want our database server to be perceived as, since all of these create comprehensive service level agreements that are not always the ones that are not similar. Let me rephrase that are not similar to the ones that are provided in other fully managed database services in the market. In terms of security, we have automated security processes, and we are also compliant with a body of certifications either provided by Azure, by the International Standards Organization, or by external policies, including HIPAA compliance and GDPR compliance. So we have our security team always constantly monitoring and constantly enabling security certifications. The certifications are a guarantee of security standards that keep getting updated. So we're always up to date with these standards as they come out. Compared to hosting your own database system, this greatly simplifies the security management, since it's now guaranteed, or it's now a process that the cloud provider manages. We provide encryption at rest and in transit by always keeping encrypted communication channels. We have enabled encryption automatically. So all of the benchmarks, all of the cost associations, and all of the implications assume that the encryption is enabled. We have a comprehensive set of certifications, as I mentioned, and we also provide IP whitelisting through a firewall that is enabled on all database accounts. We provide virtual network integration, which allows you to use all of the other resources within your Azure virtual network and have them exclusively communicate to Cosmos DB, also configurable to subsets of the virtual networks, as well as increasing IP ranges within the virtual networks. And we provide key-based authentication, and Cosmos DB automatically rotates the keys when necessary if one of the keys in the application has been detected to be compromised. We have a difference between read-only and read-write keys as well. So in summary, the following are the reasons why customers like to use Cosmos DB and why there are different scenarios that benefit from Cosmos DB. First of all, is the first and only database with the global distribution capability in a turnkey basis, meaning that it's just a configuration setting to add a different region and enable all those replication mechanisms. It delivers massive storage and throughput through easy to configure parameters. Our throughput measure is just how many requests in a second you want your database to provide. So it saves up all of that planning and all of that capacity estimation that requires to deal with physical resources and physical infrastructural components. It provides single-digit millisecond latency for fundamental operations, and it is backed by a service level agreement. Supports different types of data. If you're using graph data, if you're using document data, columnar data, you can find an API that uses it and use that on Cosmos DB out of the APIs that we provide. We have 5 well-defined consistency models to really tune the scenario that you're using. If you want to build a scenario where strong consistency is important, like a financial application, then Cosmos DB will provide that guarantee from an infrastructural perspective. However, if you're building an application that needs to benefit from the highest possible performance, then you can use the eventual consistency in Cosmos DB, and it will provide that advantage. This enables mission-critical applications. We have a number of customers building their business critical applications on Cosmos DB due to all these guarantees and all of these capacity management features, as well as the differentiating features of Cosmos DB. So you can optimize for speed and cost, meaning that you can always adapt to your capacity and reduce the capacity if you need to optimize for lower capacity seasons. Tackles big data with its integrations for Apache Spark and data analysis platforms, and it provides enterprise-grade security by delegating the security components to the Azure team that is running the service. So it's always analytics ready and perfect for event-driven architectures through our communication pipelines and event sourcing mechanisms that allow us to connect to serverless platforms. So with that said, I wanted to provide a summary of Cosmos DB, which was this one. I'm wondering, are we going to have time for Q&A, or is this going to be handled separately?
Yeah, we can do Q&A.
Okay, perfect. So we have 5 minutes in case there are any questions.
Yep. So the first one is: are there any published how-tos on how to set up a gaming setup for Cosmos DB?
We have reference architectures and different samples for this. Since this involves multiple Azure services and Azure platforms, you'd have to find the right products that fit your needs. But we provide reference architectures that will give an idea of that. Maybe not as much as a tutorial per se, because it's a comprehensive system that has many implications. But the reference architecture is a great starting point for this, and you can find that at gotcosmos.com. Cosmos.com. I can share the link afterwards. It has all of our customer references and architectures that can be followed publicly.
Great. Are there papers or guides for telemetry stores? Stores for IoT. How secure would the data transfers be?
The data transfer depends on the pipelines that are used. In this case, in the reference that I shared, we use IoT Hub, which is an event sourcing mechanism that, depending on the tier of services, you can also provide authenticated connections to IoT Hub. Then between it, we have Apache Storm, but this is now under Azure internal components that are communicating with each other. So that provides an additional level of guarantees. Again, all customer references and reference architectures can be found at gotcosmos.com, which contains the architectural guidelines to host these kinds of systems. And we do have one for IoT and telemetry.
Okay. Can we store data in Cosmos DB in one format and get data back in another format, like store data as tables and get data back as a graph?
Right. Currently, the only APIs that are interoperable are the Graph one and the SQL API one. This is not the case for any other of the APIs.
Okay. Was the size of the document store increased? We tried Document DB over 2 years ago, and we were limited on the size and went away from the technology.
I'm guessing the individual size of the documents. And so for that case, our limit is 2 megabytes, which is probably the same limit that was there before. And this is because we're optimized for applications that make use of requests that require less than 2 megabyte operations. So telemetry, IoT, gaming, e-commerce, etc. Cosmos DB is not meant to be a large document store, for which we recommend solutions like embedding permalinks or links to an blob storage account. So you can store your large files on blob storage and then keep the reference and the permanent link from them in Cosmos DB along with other metadata.
Okay, one last question. Can we use Cosmos DB to replace Elasticsearch use case?
So Elasticsearch is interesting because it provides a set of search capabilities that may not be available directly in Cosmos DB. We recommend using our Azure Search plus Cosmos DB integration, which will allow for things like full text search, and building custom indices based on specific queries. So that's what the equivalency would be.
Okay. Great. Well, that was the last question. So thank you so much for Luis for getting up early and presenting with us. Thank you everyone for attending. The 9 o'clock session is just getting started, so feel free to jump over there, and we'll see you on the next one. Thank you again, everybody.
Thanks, everyone.